Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be looking at Unit number 6, Lesson number 8 on trigonometric equations. Again, if this is your first exposure to solving a trig equation, this is probably not the lesson that you want to be working on, because this is based on the idea that you've seen extensive trig equation solving in a previous course. But let's launch right into it. We're going to be concentrating on algebraic methods today, but we are going to do one graphical problem, so make sure to have your graphing calculator available. All right, let's take a look at exercise number 1. This is kind of a classic, and I designated it as non-calculator. It asks us to find all values of x between 0 and 2 pi that satisfy the equation 2 cosine x times sine x plus cosine x equals 0. Now, it is really important. A lot of students say, do something like this. They decide to swing that sort of addition by cosine over to the other side, and then they kind of cancel a cosine out. Don't do that. Never, ever, ever divide a variable out from both sides of the equation. Bad idea. You almost always lose roots. So I'm going to scrub that out. In fact, if you've got an equation set equal to 0 and you know you're going to be doing an algebraic approach, perhaps the best thing to try is a little zero product law, right? So if I factor a cosine out of both of those two expressions in that binomial, I end up getting this equivalent product. And of course, the beauty of the zero product law is that I can either take cosine x and set it equal to 0, or take 2 times sine x plus 1 and set it equal to 0. Doing a little bit more work on this, I'll get sine x equals negative 1/2. Now, it's very important for us to keep our interval in mind. It's not always just about the equation, it's also about the interval. So I think to myself, as I go around that unit circle once, right, from 0 to 2 pi, where do I hit an angle that has a cosine of 0? Well, that's going to happen at pi over 2, and it's going to happen at 3 pi over 2. So there are two of my solutions. I also have to ask myself, where am I going to hit a sine value of negative 1/2? Now, traditionally, this is how you would have learned to do it, and this is great. You think about a reference angle, right? The reference angle will literally be the inverse sine of positive 1/2, which based on the previous lesson would be pi over 6. Then we say, yeah, but sine is negative in the third quadrant and the fourth quadrant. So if we start at 0, right, and we rotate, and we get to a reference angle of pi over 6 in our third and fourth quadrants, then one of our angles will be pi plus pi over 6, which will be 7 pi over 6, and the other angle will be 2 pi minus pi over 6, or 11 pi over 6. 4 solutions. It's not unusual for trigonometric equations to have a lot of solutions. Honestly, if we didn't have the interval 0 to 2 pi there, we'd have an infinite number of solutions, and that's because of the periodic nature of sine and cosine. So why don't you go ahead and write down that text. I'm going to get rid of it in just a second. All right, going to scrub it out, and it's gone. Moving on. Let's take a look at the messiest problem we're going to see today. Exercise 2 says, solve the following equation in 2 ways, one way algebraically and one way graphically. Round all answers to the nearest hundredth of a radian. So this is going to be ugly. Let's take a look at 5 sine x plus 2 equals 0, where we're between negative 2 pi and 2 pi. 2 full rotations around that unit circle. Well, one thing that we can definitely do is we can definitely solve this equation for sine, and that's easy enough, right? We get sine x equals negative 2/5. Now what I'd like to do is I'd like to get a reference angle, an angle between 0 and pi over 2 that has a sine of positive 2/5. Now this is definitely something that we have to do on our calculator. And if we want it to be accurate, when they say round our final answer to the nearest hundredth of the radian, we would want to round this 1 decimal place further. Now according to my answers, that's 0.412. Okay, that's our reference. I know it's weird. I know it's not in terms of pi. Now, let's think about what our actual answers are. Sine is negative, as in the last problem, in the third and the fourth quadrant. Now I'm going to draw the little unit circle. Now I really need to take 2 trips around this circle, and I really should start at negative 2 pi and go to 0, and then go from 0 to 2 pi. But for a second, I'm going to just take the first trip around the circle. Okay, I'm going to go from 0 to 2 pi. All right. Now, on my first trip around, from 0 to 2 pi, what I know is that that angle is 0.412. So one of my x values is going to be pi plus 0.412. And again, this is kind of a messy answer, so I'm going to look over, and I'm going to find it's 3.55 radians. If I continue around the circle, my next one is going to occur at 2 pi minus 0.412. And again, taking a look, that's 5.87. All right. The question is, how do we get these? Negative 2 pi to 0. Well, there's a bunch of different ways that you could do it, right? One way to do it is you could say, well, forget about that. Let's just assume I'm at negative 2 pi. Now let's travel around. By the time you've gotten to here, you're at negative pi, and then you go another 0.412. So one of the angles would be negative pi plus 0.412, right? Because we're not going to quite have a full negative pi, and in fact, that's going to give me negative 2.73. Sorry, I'm not wearing my glasses. And likewise, if we keep going, right, if we go all the way to here before we get back to 0, we're just going to be at negative 0.412, but once I round it, negative 0.41. All right, we're going to look at this a little bit more once we get into the next set of problems, but hopefully that makes some sense. Now, another way to do this is to do it graphically, and I claim in this particular scenario the graphical solution makes as much, if not more, sense than the algebraic. You see, I needed to use my calculator to come up with those 4 answers anyway, so why not just solve it graphically, right? So that's what I'm going to do. I'm going to open up my calculator now. Okay, here we go. I'm going to go up to y equals. All right, if I have any equations in there, I'll clear them out. And then in y1, let me write this down actually on the sheet. On y1, I'm going to put in 5 times the sine of x plus 2. So let me put that in. 5 sine function x, make sure those parentheses are closed, right? We don't want the 2 inside of them, plus 2. Okay, I got it. Now, of course, I want to make sure that I get all 4 of my answers, so I have to pay attention to my window, right? So let me go into my window setting. A little bit tricky. Go to xmin and I type in negative 2. Now I got to get the pi. Okay, now I'll go into my maximum and go positive 2 pi. Okay. Now what my y window should be, that I can actually think about. We know that we have a midline of 2 and an amplitude of 5, so we must go as high as 7, so maybe I'll just set my max at 10. And then I know that I have a min of negative 3, so maybe set my min at negative 5. Great. Now let me hit graph. Takes a little bit for the graph to come up on the screen. All right. Now given that I'm trying to figure out where this equation is equal to 0, I should use the 0 command. I'm not going to use it for all 4. We'll just illustrate it on one of them. Why don't we go for that first positive 0? All right, so go into my 0 command. All right, 0 is sometimes frustrating for students. Remember, it asks for a left bound, so you put the cursor somewhere to the left of your 0, hit enter. Then it asks for a right bound, so we're going to put our cursor somewhere to the right of 0 and hit enter. All right, great. And enter for the guess. And take a look at how that compares to our actual 0, well, to our 0 that we found algebraically of 3.55. Maybe write that a bit better. The box got it. All right. So I claim that a graphical solution is a really, really good solution on this because you can find all 4 zeros, you can find them easily, and you don't miss any of them. Assuming you have a good window set. All right, I'm going to be clearing this out, and the calculator is going to be going bye-bye, so copy down anything that you need to. All right, let's go on to the next page. From now on out, we're going to be solving everything without the calculator, and what we're going to be getting into are what I would call variable frequency trig equations. These are very, very important. So these are trig equations where what we have inside of here isn't just a single x. It's 3x, it's 1/2 x, it's whatever. These types of equations come up somewhat frequently on the AP exam, and I want to really kind of emphasize something. Now this is going to sound really dumb, but I have my students repeat it over and over again. I want you to look inside of that sine function. What you see is you see 3x, and 3x is what we're taking the sine of. So that is actually the angle. That's the angle. Okay, x is not the angle. 3x is the angle. So what I always ask students to do when they do a problem like this is immediately, whoops, that isn't there. Let me get rid of that little equal sign. Back to my pen. I ask them to write out an interval for whatever the angle is. I hope it makes sense to you that if x's smallest value is 0, then 3x's smallest value is 0. And if x's largest value is 2 pi, then 3x's largest value is 6 pi. Hone in on that. The angle is 3x. Don't worry about x. We'll eventually find it. So let's solve for 3x. I can easily isolate the sign, and I'll get sine of 3x is equal to negative root 3 over 2. Now I'm tempted to put down x sub r for reference, but I'm not going to do that. I'm just going to put down reference angle, right? What angle has a sine of root 3 over 2? Think about that for a minute. Okay. Hopefully pi over 3. Also, man, we have a lot of these, don't we? I should get a little bit, right? Also, we must be in quadrant 3 and quadrant 4 because sine is negative. All right, so let's think about this. We have to go around the unit circle 3 times, right? Because I have to go 0 to 6 pi. The first time I hit a pi over 3 in quadrant 3 is going to be at 5 pi over 3. No, sorry, at 4 pi over 3. That's the one in my 4th quadrant. Let's try that again. At 4 pi over 3. Right, so that's my 3rd quadrant. And in my 4th quadrant, I have 5 pi over 3. So that puts me around the unit circle once. Now, I'm going to draw a little diagram. Right, so my unit circle, I went around it once, and I ended up, at theta equals 4 pi over 3, and then I kept going, and I ended up being at theta equals 5 pi over 3. But then I keep going, and I'm going to put the rest of this sort of like trip in red, right? So I keep going, because I have to go all the way to 6 pi, and I hit the angle again, and I hit this one again. The question is, what do I have to do to this 4 pi over 3 to get to my next angle? I know that kind of looks like a little bit of 9 pi over 3, but if I try to erase it, that's what happens. Let me put that in there, 4 pi over 3, and now it's in red. Anyway, what do I have to add on to that 4 pi over 3 to get to the next angle over? You have to add on 2 pi. Now I know this causes you to add fractions, but it's not that bad, right? If I do 4 pi over 3 plus 6 pi over 3, which is the same as 2 pi, I'll get 10 pi over 3. And if I add 6 pi over 3 to this one, I'll get 11 pi over 3. That puts me around the unit circle twice. Let's go one more time, maybe another color. Obviously, as I go around again, I hit it one more time, right? And this time I'll add another 2 pi and another 2 pi. You'd think I could get all this on the same line, but I just can't, right? So the next one would be 16 pi over 3, and then 17 pi over 3. Whew. Now, watch out, because we're not quite done yet. In fact, what we just figured out were the six values for 3x. What we now need are the 6 values for x. But we can easily solve for those by dividing both sides of the equation by 3, although quite frankly, since there's so many fractions involved, I would suggest multiplying both sides of the equation by 1/3. And then what we get is our solutions. Look at these. 4 pi over 9, 5 pi over 9, 10 pi over 9, 11 pi over 9, 16 pi over 9, and 17 pi over 9. Notice, by the way, that 17 pi over 9 is just shy of 18 pi over 9, which equals 2 pi, and that was our upper bound for x. All right, so make sure at the end of the day when you solve a trig equation that all of your solutions lie between the bounds that they give you for x, or whatever your input value is. All right, write that down. I'm going to scrub out the text. Beautiful looking picture, a multicolored Ferris wheel. Here we go. All right, next trig equation. Let's do one with tangent. Tangent. Okay, notice we have tangent 1/2 alpha equals -1. So immediately what I'd be doing is I'd say, all right, well, if alpha goes between -2 pi and +2 pi, then 1/2 alpha will be going between -pi and pi. Remember, 1/2 alpha is your angle. Now you think to yourself, well, I need a reference angle. So I think about tangent equaling +1. Right? What's our reference angle? What angle between 0 and between 0 and pi over 2 has a tangent of 1? Pi over 4. Maybe the most important special tangent value out there, pi over 4. But tangent is negative. What quadrant are we in if tangent is negative? I want you to pause the video and really think about this because we haven't had to consider it really this year. Okay, well, we considered it a little bit in the last lesson, but tangent is going to be negative in quadrant 2 and quadrant 4, wherever sine and cosine have opposite signs. So, all right, now this is a little tricky, right? Because you really want to visualize the right path. You are starting at -pi on the unit circle, and you're moving around to +pi. And we are
Attention HARP members, please meet at the flagpole entrance. Thank you.
Okay. We are here, right? We've got these two angles in the second quadrant and the fourth quadrant. But we're starting here, right? So as we travel around and we get to this angle, where are we at? All right. We're at -pi over 4. Think about having a number line, right? If I had a number line that stretched, if I unwound this number line, right, and it went from -pi to +pi, right, with 0 being right in between, I'm hitting my first value right here at -pi over 4. As I continue around here, right, I hit my next value at +3 pi over 4. And then I'm done, because I went from -pi to pi. So what I know now is that 1/2 alpha is either -pi over 4 or +3 pi over 4. To figure out what alpha is, I'll multiply both sides by 2, and I'll find alpha is -pi over 2 and 3 pi over 2. Both of which fall very nicely within my original interval, right? It's got to be the original interval. Okay. Again, going to scrub out the text. Oh, I guess I got to leave. No. That was just the end of 7th period bell for those of you at Arlington. The hallways are now going to get loud. So let's see if we can move on to the, I think, last problem. Yes. Solve the equation secant squared of 2 alpha equals 2 for all values of x. Well, that's weird. Let's do all values of alpha on the interval -pi is less than or equal, is less than alpha is less than pi. All right, well, first off, let's change this, right? We have -2 pi and +2 pi. Okay, so 2 trips around the unit circle, and boy, are we going to have a lot of solutions. And let's take a look at why. Right? One logical thing to do immediately in this problem is to take the square root of both sides. So if I take the square root of both sides, I will get secant of 2 alpha equals plus or minus √2. That may be a special angle that, or a special value for secant that you know, but probably not. Most of you will probably rewrite this as the following. The cosine of 2 alpha would be plus or minus 1 divided by √2, which is plus or minus root 2 over 2. So now I bet the reference angle is clear. What's the reference angle? Pi over 4? Good. I hope that's what you had. Ooh. And what quadrants am I in? What quadrants am I in? Hopefully, all of them. All quadrants. Now, think about that for a second. We're in all quadrants. So, we're going to start it, and we're at all quadrants with the angle being like 45 degrees, pi over 4. So I'm going to actually sketch in my angles first, and watch this. Right, I'm at negative 2 pi. Oops, sorry. That's just silly. Thinking about the last problem. I'm at negative 2 pi. I'm going to go around the circle until I get to 0. And then I'm going to go around the circle again until I get to 2 pi. Sorry about how terrible that drawing looks. So, wow. That's a lot of solutions. Think about how many solutions I'm going to have. Just think about that for a moment. Hopefully what you figured out is that I'm going to end up having 8 solutions. Why don't we concentrate on the ones that are between 0 and 2 pi just first? Okay, now remember, that's what 2 alpha is going to be. So let me put it here. Well, we're going to get pi over 4. We're going to get 3 pi over 4. We're going to get 5 pi over 4. And we're going to get 7 pi over 4. Now, let's also think about the ones that we get from negative 2 pi to 0. It's okay to travel this way, by the way. And the nice thing about that is that we would very quickly understand that we're going to get negative pi over 4, negative 3 pi over 4, negative 5 pi over 4, and negative 7 pi over 4. Wow. But that's what we have for twice alpha. Multiplying both sides by 1/2 gives me, and I'm going to combine some answers now, plus or minus pi over 8, plus or minus 3 pi over 8, plus minus 5 pi over 8, and plus minus 7 pi over 8. Wow, 8 solutions. No great surprise, we've sped the curve up, and the fact that we've squared it automatically doubles the number of answers. So, yet again, going to scrub out the text, pause the video now if you need to copy anything down. Okay, let's go on to the next the next sheet before the final bell rings. All right. Well, that was another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler. As always, you can get the worksheet and the homework for this lesson by clicking on the video's description underneath the YouTube video. Until next time, keep thinking and keep solving problems.